Hey everybody, welcome to Data Platform Summit 2020. Today, you and we're going to be talking about optimizing backup performance via data science techniques. So my name is Kevin Feasel. I run a predictive analytics team, also a Microsoft Data Platform MVP out of Durham, North Carolina. I have a blog called Curated SQL. The idea of Curated SQL is that I want to try to find and link to 5 to 10 interesting posts per day on topics like database development or administration, R, Python, Hadoop, Scala, Spark, Power BI, reporting services, security, or anything else in that broad data platform space. That's curatedsql.com. My question for you today is, how big is your backup window? So how much time do you have to perform full backups? If you have all the time in the world, okay, that's fair. Or if your backup window is several hours, but it only takes you a few minutes to back up all of your databases, yeah, probably don't have to worry too much about this session. But suppose that you're in the opposite scenario. You have a 4-hour fixed window and, well, you're not fitting all your backups in that 4-hour window. It may take 4 or 5 hours to back up one database. Perhaps that's impacting other performance of applications. So if you are in that situation where your backup window just feels a little too tight, I may have something that could help you out. What I want to do is use existing data science techniques to minimize the amount of time that it takes to back up our databases. This way, we can back up those databases faster, but also use the same technique to restore databases faster as well. And this is, by faster, what I mean is faster than the defaults. If I just say backup database, it's going to take a certain amount of time. I want to try to tweak this so that it takes less time than that default. So our first point on the agenda is, as in any data science project, we have to describe the problem, understand what's going on. Backups and restores are critical for DBAs, but it can take a lot of time to back up a large database. When we start talking in terms of terabytes, it could be hours and hours before that backup is finished. If I don't have hours and hours for a full backup, you can run into trouble as databases grow. So what options do we have available to us? Well, we've got a few of them. One idea would be to use read-only file groups. The idea here is that if we have, say, a majority of the data that just never changes, I can take a backup of that file group and keep it, but I don't have to keep backing that file group up because I have a good copy. Then, if that does change, I'll take a new backup afterward. If that's a majority of our data, we may be out of the woods for that database. We could use newer editions of SQL Server. 2017 in particular had several changes which affected backup performance and made it a bit faster. We can get rid of obsolete tables. It may turn out that you just have a lot of data, which is simply not necessary. Getting rid of that data considerably shrink the backup window size, considerably shrinks how long it takes to back up that database. We can also use techniques like data compression. If I compress, especially with page level compression or column store compression, where that makes sense, I can reduce the size of data on disk, and that's also going to impact the size of a backup because it's backing up the compressed data. It doesn't need to decompress and then back up. So that can reduce the time it takes quite a bit as well. This is separate from backup compression. Backup compression is a different story. We will talk about that as well. We can split data across multiple file groups and back up those file groups separately. So we may have different windows for different file groups. The read-only file group example is just one scenario of this more general case. We can use differential backups. Instead of taking a full backup every night, perhaps we take a full backup once a week when we have a larger window available to us. and then differentials during the week when we have to keep it a little snappier. The last thing that we can do is configure backup settings. Well, that's going to be our focus for today, where I'll talk to you about what those backup settings are, what they represent, and how we can take advantage of them. So the next step in our agenda is to look at these settings. Backing up a database is pretty easy when you think about it. The syntax is just on the screen right here. Backup database to disk with no format and init. Now, no format, by the way, means that we want to preserve the existing media header. So I don't need to create a new one. Init says if you have backups already in this file, get rid of them. So overwrite any existing backup sets in that .back file. In practice, you can write multiple backup sets to a single file, but I generally don't like that very much for a couple of reasons. One is logistics. If I want to manage my backups and get rid of them after a certain amount of time, I'd rather have that be separate files where I can manage that in the file system. Also, if I need to restore from a specific point in time, it's easier for me to find that in a file system than trying to find a backup set which has that date. So it's a little bit easier for me to work with separate files and build out a restore statement from there. Our first major setting is block size. This is the physical block size for a backup media. In fairness, this really only matters if you're using tape. I guess if you were backing up to CD, this would also matter. But if you're backing up to CD, you don't care about performance anyhow because that's already way slow. The valid set of values, enumerated right here, everything from 512 bytes up to 64 kilobytes. And this is the exact set of valid values. Max transfer size is the maximum amount of data to be transferred per operation. Technically, you can think of it as the size of a buffer. In allegorical terms, think of it as the size of a bucket. So if I'm taking data from a database and backing it up, you can think of this as I'm going to turn on the spigot and data is going to pour out into my bucket. And I take that bucket and move it away somewhere, pour it into a tank, and that tank is representing my backup. So this is how big my bucket is. Everything from 64 kilobytes up to 4 megabytes. And again, this is the exact set of valid values. No other values are considered valid. Buffer count, the max number of buffers of size, max transfer size. So in other words, how many buckets do I have? Continuing that metaphor from the last slide. Unlike the previous two examples, this is just an integer. Anything from 1 to 1,000,000. But I would recommend you try to stay at or below roughly 1,024. Because if you have 1,024 buffers and a 4 megabyte max transfer size, you are creating 4 gigabytes of memory utilization for a single backup. Now, if you work with a medium-sized server, say less than about 64 gigs of RAM, 96 gigs of RAM, 4 gigs just for a single database backup is a lot. Even if you're talking about a mega server where you have hundreds of terabytes or petabytes worth of data stored, you don't need that much RAM to take a backup, because really all you're needing to do is have enough so that you don't run out of buffers as you're backing up, as you're writing to disk. So this number generally doesn't need to be that high. File count tells you to stripe your backup across multiple files. This is a really good way of getting extra throughput and will heavily depend on if you have direct attached storage, how many separate drives you have, and if you have a SAN, how much available bandwidth do you have? In practice, there's a number of files per disk that you'll probably find will be nice. That number may be about 12. 12 is a first order estimation. So if you have one drive that you're writing to, you can usually get better performance by writing multiple files up to maybe 12. But again, it's going to depend a lot on the type of drive. It's going to depend on how heavily it's utilized. It's going to depend on several other factors. Compression. Do you want SQL Server to compress the backup? This is separate from page level compression of a table or an index. This is separate from column store indexes. This does have a CPU cost, but typically leads to smaller backups. Generally, I default to true. However, there are cases with larger databases or with certain types of data structure where you have a lot of, say, binary data, for example, where compression may not necessarily make sense. Features used can also play a role in this. If you're running prior to SQL Server 2016 and you have transparent data encryption turned on, you don't want to compress the backup because you would be compressing a backup that is already encrypted. As of somewhere later on, I believe it was a service pack in 2016 and a CU in 2017, that was fixed to where compression happens first and then encryption. So late editions of SQL Server that are well patched and updated, you could have TDE and compression and not lose anything as a result. So with our additional settings, this gets a little bit more complicated. Our backup statement now has a bit more heft to it. So we can write to multiple backup files, increasing disk throughput. I have an example here of just 2 files, but like I said, you can have many files. There's a trade-off, of course. When you restore, you need to specify all of those files. But if you're writing a script or have a job to perform restoration, that's not too big of a deal. Max transfer size, 2 megabytes here. So it's going to use 2 megabytes of RAM per buffer. We're going to use 50 buffers in total. So that'll take 100 megabytes of RAM to run through. Our block size, 8 kilobytes. And I've turned on compression. So great, now that I've given you these numbers, these are the right settings for everybody, yeah? Well, not that easy. So it turns out that we can change each of these settings, but there are a lot of values, and the specific set of values that work will depend on your hardware, your workload, and factors specific to your environment that I can't predict. So I can't give you numbers. What I can give you is a process, a technique for finding out what numbers work best for you. Let's learn that technique. That technique includes the power of sampling. Because you see, supposing that I give you all of the block sizes, all of the max transfer sizes, a fairly small sampling of buffer counts, a fairly small sampling of file counts, and don't even try no compression, just always compress. Well, that gives us 3,136 separate options. Now, suppose it takes you about 10 minutes to back up a database. By the way, if it's taking you less than 10 minutes to back up a database, this may not be that important for you. Unless you have an extreme number of databases, then it could still be a factor. But if it's taking you just a few minutes to back up a database, unless that's heavily impacting customer performance, I wouldn't be too concerned. So this is a low estimation on time. In reality, we're talking more about, well, my backup is taking 8 hours, 12 hours, 14 hours. But let's just say it takes 10 minutes. At 10 minutes per backup, 3,136 backups is about 31,360 minutes, or roughly 22 days of just running backups. After that point, I can find what combination of these 5 attributes is best and use it for my database. But That's a lot of work to get to that one point. So what I'd like to do instead is look for a smaller number. I can combine DBA tools to perform my backups with some simple PowerShell to sample these settings for our databases. That way, I don't do 3,136 separate backups. I do a much smaller number, but still generates enough results that I will be able to apply data science techniques to the full data set. So let's take a look at that script. And I'm going to pull up Visual Studio Code that already has my simple backup options right here. This, by the way, is a gist for this function Cartesian product. The Cartesian product function is essentially a cross join in PowerShell. So it's up there. I'm going to hit a local instance name, so localhost, and some database name. Here for my sample data, I generated it off of various sizes of Stack Overflow and a few other databases. So what I'm saying is, for each entry in the Cartesian product of my block sizes, my buffer counts, my max transfer sizes, my file counts, that's 3,136 possible options. So for each one of those 3,136 options, let's get about 100 samples. 100 is going to be enough for me to draw some reasonable conclusions statistically, even if I may miss something. Even if I may have some gaps, it's going to be a pretty high probability that I'll have enough information to take this sample of data and apply its results to the whole population without losing too much. So what I'm going to do is generate a random number. And what I'm taking advantage of is the fact that getRandom follows a uniform distribution. So if I say maximum 100, that's going to generate a number from 1 to 100. And what I can do is, all right, well, if that random number is 97, 98, or 99, we're going to take a backup. So 3% of my results. I got that because I said I want about 100, and so I take 3136. 100 divided by 3136 is about 3%. So I need to take backups about 3% of the time. And I just chose if it's greater than 96. I mean, frankly, I could have just said if the random number is 1, 17, or 48. Maybe those are lucky numbers for you. That will give you the same outcome because it's a uniform distribution. You are equally likely to get any one of those 100 numbers. So it doesn't matter which specific numbers you chose. But if we land on one of those lucky numbers, we perform backup DBA database. This is part of the DBA tools set of PowerShell scripts. And I can pass in my SQL instance name, my backup directory. Yeah, I did back it up to the C drive for this demo. The databases were on a different drive, so it wasn't backing up to the same drive as I wrote everything to. So it still gave me some reasonable numbers. Pick my database name, full copy only backups. And like I said, I'm going to force compression. I won't even give it an option. Just for these demos, I'm going to turn compression on. That simplifies my set of options. It cuts in half the number of backups I need to take. But it does limit me to just telling you the information that I gathered solely depends on compression. I can't tell you what it looks like with compression off. It may turn out to be faster. So this is a risk I'm willing to take because my expectation is, given my computer, given my circumstances, compression is going to help us. Then I pass in the buffer count the file count, the max transfer size, and the block size. That's how easy DBA tools makes it. Most of this script is really just figuring out, do I want to take a backup, and then writing the backup and getting the timings for it. So I tracked how long it took to take that backup, which is part of the output of backup DBA database. So again, makes it really easy for me to follow along. So running that, I ended up generating some results, and we'll see those results in a moment. The first thing we got to talk about, though, is how we're going to make use of this data. So, analysis time. Well, we want to solve a regression problem. A regression problem says I have a label, I have inputs, and I want to predict the label given those inputs. Or let me rephrase that a little bit. I have a set of actual values. For example, how many seconds did it take to back up this database? That is, in data science terms, a label. I want to predict that. And I have historical data that says, well, given these inputs, this block size, this buffer count, max transfer size, compression, number of files, here's how many seconds it took to back up that database. And I could try it with different combinations of things and get differing amounts of time. So what I'd like to do is say, well, if I tell you what the block size and the max transfer size and the buffer count and the file count are, how long would I expect it to take to back up that database? So this is what we're doing with regression. And we're kind of going at it in two different ways. That's sort of the predictive side of it. The descriptive side of regression is, if I know how long it took and I know what these values were, how important are these values? Because some of the inputs are more important than others. So I want to have a weight of each value. And there are a few techniques for us to generate a regression output. One option is linear regression. Linear regression, pretty straightforward. All of the dots in this picture are actual data points. That gray line, which runs through the course of this picture, is a representation of the data. It's a representation of the shape of that data. So the line is, generally slanted kind of upwards, sort of like this. That gives us an impression of, given these two inputs, GDP, normalized to 2005 US dollars, and longevity. Here's how long we would expect people in a specific country in a specific time to live. Another option that we can follow is decision trees. A decision tree, we're pretty familiar with this in the computer science world. It's just a series of nested if-else statements. If the database is less than 50 gigabytes, and the memory usage is less than 32 megabytes, and the file count is less than 10, then something. So decision trees are nothing more than if-else statements. Random forests are a series of decision trees. What you can think of is, I have a decision tree that's made up based off of data. Well, what happens if I reduce the number of data points? I change the set of input data points. I say you're only allowed to go 2 levels deep, no deeper than that. Or you must go more than 3 levels deep. Or you're not allowed to use this as an input feature. So what we're doing is we're changing the set of inputs, and we're generating a lot of different decision trees. And then we're going to ask all of these decision trees the same question. Given this input, what do you expect the output to look like? And then we're going to aggregate together their answers and figure out what is the closest to a consensus answer that we can get. That's a random forest description in a very brief, high-level explanation. I did also mention neural networks. I'm not going to show you any neural networks here, but you can certainly use neural networks to perform regression. So now, let's go over to a Jupyter notebook and learn a bit more about this problem. My Jupyter notebook is here. This notebook, I'll have a link to it so that you can grab a copy of it yourself. There's a lot of text, explanatory text, because I want to make sure that everyone's following along, even if you don't see the presentation, even if you don't have the slides in front of you. So this kind of tells us where we're at so far. The language for this is R. So this is a R programming language notebook. And we're going to load a few packages in R. The first package here is called the tidyverse. The tidyverse is an opinionated set of packages intended to get us toward what is called tidy data. Tidy data, essentially think of it as kind of third normal form and then denormalized to flatten things out. So it's pretty close to what we would work toward in building reports. The random forest package does what it sounds like. It helps you build out random forest models. Parent is a package that will assist us in partitioning training versus test data. And it does other helpers for data science projects. EV tree lets us build expected value trees using evolutionary learning, specifically something called genetic algorithms. You are interested in genetic algorithms? I do have an older talk on the topic. Not that many people are interested in them anymore. Neural networks have sort of taken over that space. But there are places like this where I think evolutionary trees do still make sense. So I'm going to load those packages. I've already downloaded them, so it's very fast to load them up. Next, we'd like to load data from a half dozen different data sources. So this first one, the set of BAC databases, this was a database that I had access to, and there are 4 different sizes of it, ranging from 136 gigabytes down to 31. The full database is actually 136 gigabytes. After I removed the largest table, that got it down to 89. Then I removed the next largest table, down to 58. Then I removed the next largest table, down to 31. The gist here is that this is a real production database, but I wanted different sizes of data. So my thought is, well, we're going to have larger databases take longer to back up than smaller databases. So I wanted that to be factored into our analysis. I also have 2 versions of the Stack Overflow database. One of them is a tiny version that is approximately 10 gigabytes in size. The other one is a backup from 2013 when the Stack Overflow database was about 50 gigabytes in size. There are much larger backups of Stack Overflow's database to the point where I couldn't get them to back up on my machine because I didn't have enough space. But I think these set of backups will be enough for us to learn some interesting things today. I'm going to add a new feature for each of them because what each one of them has is the block size, the buffer count, the max transfer size, the file count, and the duration in seconds that it took to take that particular backup. So I'm going to add to it the database size as well, and I'll use a function called row binding. The idea is that I will take all of the rows in each one of those backups and combine them together. So think of it as union all. It's a union all of these sets of data because they have the same shape. This is really easy to do. And I'll create backup stats. From there, I'm going to convert block size to kilobytes, so divide it by 1024. This is a linear transformation, so it doesn't actually affect the end results. But it does make it easier for me to read. Then I'm going to create memory usage in megabytes and seconds per gigabyte. So let me talk through those a little bit. In an earlier version of this talk, I generated some tests where I looked at buffer count and max transfer size separately and told a whole story about how the combination of the two is much more important than the individual. And by having them separated out, it actually confused the model a bit. So by breaking those two out, we didn't get as good a model as we could have gotten. Memory amount is actually more important than the breakdown of number of buffers versus max transfer size. So that is a much more important variable. In other words, the difference between 7 buffers at 4 megabytes versus 14 buffers at 2 megabytes versus 28 buffers at 1 megabyte is so insignificant that it really doesn't affect our runtime. If there is a factor, if there is a difference, it is so negligible that we can't tell. What does make a lot of difference, though, is using 1 megabyte of RAM versus 10 megabytes of RAM versus 100 megabytes of RAM. So the combination of buffer count and max transfer size matters a lot. The components, what specific values they hold, don't matter as much. So that's why I'm going to take max transfer size, turn it into megabytes, and then multiply it by buffer count. The other thing that I'm doing is creating a measure of seconds per gigabyte. We are going to take, we have the number of gigabytes and we have the number of seconds. And you might initially think of gigabytes per second as throughput. So we have our measure of throughput and we want to maximize throughput. But really, we want to think more about seconds per gigabyte because I want to try to find a way to minimize the number of seconds it takes to crunch a gigabyte of data. And it turns out for the model that seconds per gigabyte, minimizing that value is actually easier for the model to understand than maximizing gigabytes per second. So that's why I have this inverse model, the inverse of what we would normally expect. Next up, I'm going to build out some training and test data sets. So I'm setting a seed so that way all of us, when we run this, will get exactly the same results. You could change that seed, of course, and get different results and see how stable this analysis is. So we'll take our backup stats, we'll shuffle them up, and we'll get random backup stats, which is just a randomly ordered output. Then I'll use caret's create data partition function to predict for the seconds per gigabyte and basically take 70% of data as training, 30% as test, making sure that we have different combinations of seconds per gigabyte in both training and test. Because I don't necessarily want it to be that all of the training data is one set of outputs and all the test data is a different set. I want this to be a fairly broad combination where we see things in training, we see things in test, and they can be different, but they're not radically different. Because that would tell us that our population is radically different from our expectations. And in that case, we need to adjust expectations. We need to adjust our training. So I split out training and test data, and I'm going to have 381 rows in training data, 160 rows in test data. 381 isn't a huge number, but it is enough that I can survive. 160 for test, again, I can survive. Just to give you a quick look at what this data looks like. We have, for a database, it took me 63 seconds to back up a 31 gigabyte database where the block size was 4K. I had 64 megs of RAM and one file. Doing the math, that is 1.98 seconds per gigabyte. And I want to try to minimize this. I would like this to be quarter second per gigabyte as opposed to 2 seconds per gigabyte. Because the higher that number is, the longer it's taking me to process through. So, all right, let's try to build a random forest. In the random forest project, there is a random forest function, and my shape of this function is saying I would like to predict the duration as a function of block size, memory usage, file count, database size. So I told you about seconds per gigabyte. Just keep that in the back of your mind for a bit. First, I'm going to show you duration. And I include database size as a function of duration. Because frankly, the more data you have, the larger your database is, well, the more likely that it's going to take a long time to back it up. Now, in the random forest project, there's a nice function called importance that tells you what is important about that model. And here's what we see. Database size dominates. It is 2 orders of magnitude greater than anything else. File count has a negative factor. A negative factor says that not only is it basically you want fewer files, and that negative doesn't really sound right. It's basically saying this feature does not matter at all. Block size matters a tiny bit. I can believe that. Memory usage matters a little bit. I can believe that. File count? Nah, don't even worry about it. I don't really believe that. I think what's happening is database size is such an overwhelming factor that it's just destroying the other factors. Nonetheless, let's check out our model. What this tells us is that it explains 90% of the training dataset's variance. So it's an okay start. It explains 90% of the difference in backup runtimes and durations. And if I run the predict function against our test data, I'll get back our predictions. And what I can do is show you the test data along with our prediction for test data. And we can do sort of a sanity check. So for example, this first one took 19 seconds, but the model predicted it would take 82 seconds. Well, that's way off. Second one took 203 seconds, but we predicted 201. That's really good. This one's really good. This one's okay. This is 4 seconds off, not too bad. This is 5 seconds off, not too bad. Now, what I've just did there is okay for a first glance, but it is not a scientifically prudent method for understanding how good our prediction was. And so we need measures for that. One of the measures that is common is root mean squared error. This is the formula for root mean squared error. And what it gives us is a number that represents the expected difference between duration and prediction in the unit of duration. So our prediction is somewhere around 26 seconds off. That's actually not that good, considering that our durations generally ranged. Well, let me give you an idea. Our durations maxed out at just over 300 seconds. So being off by 20 some seconds isn't great. And here's the outcome. This is our residual, the prediction minus the duration versus the actual duration. So what I'm seeing is clusters of times that I believe represent the individual databases. I say I believe because I haven't shown you that they really do. But for smaller databases, our prediction is way off. This gets a little weird where it missed. For larger databases, our prediction is way off. The prediction is best for our medium-sized databases. So it whiffs up here, it whiffs down here. It's not a very good model. Let's try a new model. This time, instead of duration, we're going to look at seconds per gigabyte. I will still include database size as a factor because it turns out, even when you divide by database size, it's still a factor. And here's our new model. This is saying memory usage is important. Database size is still important. File count is important. Block size is not important. These actually match up pretty well. If you look at the guidance on block size, it does say that if you're not backing up to tape, that, well, block size isn't that important. But the other factors do matter. And this, again, comports much more with my expectations. So let's look at the model. Now, this only explains 62% of variance, but don't compare that to the 90 from before. We're looking at different measures. So the fact that we didn't explain as much variance in the measure doesn't mean that it did a worse job. So to show you what I mean, here's our set of predictions. I've generated predictions. I'm going to combine them together, look at the outcomes, and 19 seconds predicted 20. 203 predicted 199. So we're off by a few, we're off by a few, off by a few, off by a few. This already looks better, but again, like I mentioned, that eyeball test doesn't really count. So let's look at root mean squared error. In terms of duration, we're off by about 10 to 11 seconds. That is 2.5 times better than our first model. This model is better. It is considerably better. If I plot the residuals, what we see is there's a big flat line where database size doesn't really come into play. There were 2 backups that took a lot less time than we expected, and 1 backup that took a bit more time than we expected. But all the rest were within a pretty decent range. So this is a good model. I could roll with this model. I could maybe improve the model as well, but at least it gives us an idea that, yeah, we're doing okay. I can test the boundaries as well. If I suppose that I want to try a bunch of different buffer sizes and keep the rest of the values the same. Here's what it looks like. So the block size is 16K. I tried different buffer sizes and therefore different memory usage, but keep the rest the same. Here's what the prediction looks like. So what we see is it starts at 66, and then it starts dropping a bit, until we get to 53, and then it just stays at 53. What's happening here is that we are reaching the edge of a decision tree. Decision trees only work within the boundaries of the data they've seen. Because my maximum memory usage is 4096, anything above that is going to assume that it's the same as if I used 4096, because the decision tree doesn't have any other information to change its mind. So anytime my memory usage is above this amount in realms that I have not tested, it can't give me a different answer. This is going to limit your ability to infer new information given a decision tree. But at the same time, if you're using a decision tree or a random forest, do understand you shouldn't be inferring. You should be applying information that you have in the domain and the area you are already in. By contrast, if I used linear regression, I would actually keep getting different numbers. But the problem is, those numbers could be a lie. In fact, they probably are a lie, because linear regression will go out to infinity. It'll just keep on letting you predict as far out as you want. But a lot of phenomena are not truly linear. They can be linear within a prescribed range, but once you get outside that range, the shape may change drastically. And we can't know that unless we have data in that range. So what I'm getting at is, if you build out your sample and 4 gigabytes is the maximum size for memory usage, you can't understand anything beyond 4 gigabytes. If you want to understand beyond that point, you'll have to test. You'll have to sample data. You'll have to try it out. This model, whether it's a linear regression, whether it's a decision tree, if it's a neural network, will not give you a good result beyond the capabilities of the data you fed it in. Okay, so I've generated these predictions. These are all predictions. And what I was curious about was, do we have relevant cases where we maybe have a 31 gig database size and we have a certain memory usage? What does it look like? Well, just to give you an example, 30 megabytes, we predicted 66 seconds. In reality, it was 66 seconds. So, it was 62 seconds. For 120 megabytes, we predicted 58. It was really 60. For 128 megabytes, we predicted consistently 57 seconds, and in reality, it ranged 55 to 57. So what we see is that there can be differences. We can be off by a few seconds, but it's not absurd. Next, what happens if we fix the file count and block size, but change the database size? Well, if I do that, I get seconds per gigabyte in database size, and we have an interesting shape of this curve here, where we see that it seems like over a certain database size, it's taking us longer to back up. So, seconds per gigabyte at this high point for this set of backups. I should actually point out the data points instead of the curve. So for these large databases, we're getting about 2.1 or so seconds per gigabyte. For small databases, we actually have a wider variance. Here was a database that's 50 gigabytes and is taking 2.7 seconds per gigabyte. But it can be as low as 1.5 seconds per gigabyte. So database size looks like it plays a role, but it's not a dominant role. There are other factors that also affect this backup. Last bit I want to do is evolutionary trees and genetic algorithms, because so far what I've done is show you, yes, we can get to an answer. But this leads to the next question. How do I apply that answer? And that's where an evolutionary tree really helps us out. So the EV tree function, I'll feed in block size, memory usage, file count, and database size. I'll say max depth of 4 levels, and I want at least 10 buckets. Let's plot those results. And this is what it looks like. This is a fairly small tree, so it's not that horrible to read. However, I can easily read this just by running EV. And what it gives us is, here's our root. If our database is less than 50 gigabytes, and our memory usage is less than 32 megabytes, and our file count is less than 10, we're predicting 2.2 seconds per gigabyte. Well, if I increase the file count, we're predicting 1.9 seconds per gigabyte. But here's the kicker. If my database size is less than 50 gigabytes, and my memory usage is at least 32 megabytes, our seconds per gigabyte is down to 1.7. So what this is saying is, for a database that's less than 50 gigabytes in size, give me 32 megabytes of RAM for memory usage between buffer count and max transfer size. The reason why is I could give you more, but the model doesn't think that it needs more. It cut off at 32 megabytes because that's where we saw a differentiation. So more than 32 megabytes and we're just wasting memory. So I could have 2 megabyte max transfer size and 16 buffers for those databases that are less than 50 gigs. For databases at least 50 gigs, well, I want to look at these last numbers again. 2.7, 2.3, 2.2. Oh, here's the lowest number. Basically, this is saying for my larger databases, at least 50 gigabytes, make sure to have 120 megabytes. So again, if my max transfer size is 2 megs, I want 60 buffers. I shouldn't give it more because adding more doesn't help. Adding more doesn't really reduce that number very much, if at all, at least according to this model. So what I've done by reading through the model, I can now change my backup script and say, any backup that's less than 50 gigs, apply these settings. Buffer count of 16, max transfer size of 2 megabytes, don't care about block size. And we could apply file counts, but the model doesn't even care. If the database is at least 50 gigabytes, apply 60 buffers, 2 megabyte max transfer size. Now, let's see what the predictions look like. This is me building out a model. This is based off of the training data. We want to see how good those predictions are. And duration versus prediction. The eyeball test says that there are some differences, but that they're not crazy differences. Still, let's look at RMSE. 11.2. So that's a little bit off. It's a little bit worse than our random forest model. It's actually not that bad. And if I plot, what we see is something interesting. We're still kind of hovering around 0, but there's a line. There's a line that's saying, I'm probably missing a variable here. When you see a shape like this, when you see a pattern like this, that's easy to say, well, I'm missing something. And that something, I believe, is actually file count. I think that the predictions that are faster than the duration. So pred duration was, say, 80 seconds, and actual duration was less than 80 seconds. Were probably because I had more files. So this is an indicator to me that, yeah, my evolutionary model wasn't perfect. I think it missed something. And we could add to it to make it a little more accurate. But still, we have a pretty decent model. If I just used what I had there, I get much better results than if I let everything stay at the defaults. So let's wrap things up. Let's talk about, well, what do we do next? All right, what we've done so far is I showed you a variety of databases, attempting to maximize performance by using different algorithms. I showed you random forest and then an evolutionary forest. I could show you linear regression as well, but the results aren't that different. Well, the next step is reverse the process. And we started doing that with the evolutionary example. Find the output parameters that maximize performance. In my evolutionary example, like I said, for small databases, less than 50 gigs, use this combination of buffer count and max transfer size. For larger databases, use this combination. I could deploy the model somewhere, perhaps using SQL Server machine learning services, so that I can regularly train and test this model. Because it was like this today. However, if your circumstances change, maybe you get new hardware, maybe you have a different version of SQL Server, maybe your underlying data radically shifts. People start storing a lot of XML or JSON data, or you change, you get rid of a bunch of XML data. That can affect your backup performance. That could affect the model. Over the course of this talk, we've covered one data science scenario, optimizing backups. Tried out a number of algorithms, several approaches to solving the problem, and we saw how they compare. We saw the random forest, we saw the evolutionary model, we saw looking at duration versus throughput or inverse throughput. If you'd like to learn more, you want to grab the slides, you want to grab the demos, you want to get links to additional resources, go to csmore.info/on/backups. If you have any questions at all, please feel free to contact me. I've listed my Twitter handle and my email address here. And if you want to talk about consulting, maybe you want to try this and engage my services a bit more, check out that link. In the meantime, thank you so much, and I am here to take questions for the next however many minutes we have left. So with that, before I get to questions, let me just say thank you. Thank you, Microsoft, for supporting the Data Platform Geeks community initiative, for supporting Data Platform Summit. I wish I could be in person this year. Would have been a great trip, but circumstances. So doing this remotely, doing what we can. And thank you for attending. Note that there are 3 ways to win prizes. I'm sure they are fabulous prizes. Post a selfie with the hashtag DPS2020. Be sure to give some session feedback, conference feedback, and also check out sponsors and exhibitors throughout the conference. And with that, now I'm really going to say, let's go to Q&A.